All right, okay. So again, from last time, we decided the midterm was on February 8th, right? So reminder, midterm is released on February 7th to February 8th. Okay. So it's not a very long midterm, but we'll cover everything we've been doing probably up to type 3. Okay, so this week we'll start with type 3. We'll probably cover to the end of type 3. Be a lot of different equations all related to each other. Okay, so you do want to take a look, right, once it's released, and ask for any clarification question you may have. Okay, so this is a midterm. If you wait until the last second to do it, then there's a good chance you'll read the wrong equation and nothing, right? So, okay, so for the midterm, so continue from last time, right? So up until now, what we cover for the generator is we cover type 1 and type 2, right? So if you look at type 1, as a reminder, so we always have our circuit. Let's say we have this as x2 prime, r1, x1, r2 prime, and then we have a developed voltage. So this is r2 prime, s1 minus s. Right? So this is our type 1. Okay, so type 1, this is again an induction machine run backwards. And the problem with type 1 is has a very narrow operating range. You need the slip to be in a very narrow range for this machine to work, for it to be stable. So limited, the wind speed you can operate under. So type 2 was trying to address this problem. So if you look at these numbers, the number that impacts the active power most is this R2 prime number. So type 2 just says, okay, let's take R2 prime. Let's just add something to it. Right? Change this R2 prime number. And we can change this Rf prime dynamically. Then I can change the operating characteristics. I can operate at a much wider range. Okay? Right, so that's again, this week's homework is asking you to do some of these calculations. Okay? So the key here is this R add is not a constant number. Okay, so but just adding a constant number to this doesn't make a difference to this generator. This is controllable. Okay, so the key is to add a controllable resistance, so you can change the operating range of this generator. So that's for type 2, right? So type 2 still has some drawbacks, right? So anybody remember what the drawbacks for type 2 was? You can change operating range by changing this R2, by changing this RF prime. But what are the drawbacks with this strategy? Okay.
Low efficiency.
It's low efficiency, right? One is low efficiency. Because this added resistance is always used. So this is not like a resistance added for safety reasons, where you use it for a small period of time. Here you have to always add some resistance, and then you have some loss in power, right? So low efficiency. What's the other big drawback here? Okay.
It still doesn't supply any reactive power.
Right, this still has, right? So adding resistance does nothing to reactive power. Okay, you're adding a resistance. So this is still sort of cannot provide reactive power. So you use low efficiency, you're adding resistance, you cannot provide reactive power because you're not changing any of the reactive elements. X1 and X2 prime are still there. So type 3 is trying to solve these two problems. So type 3 is about sort of advanced for induction machines as you can do. Okay, so that's about as good as you can do if you use induction machine. So you look at these. So one way naively, you can think solving for reactive power, that's just adding a capacitor to the circuit. That's one way. I need reactive power, just let me add a capacitor somewhere. Why don't we do that? There's no wind turbine where you add a capacitor inside this generator circuit.
Does it have to be really big? The capacitors would have to be really big capacitors, so it'd be expensive.
Right, so capacitive elements are bulky and big. So capacitor, you look at the capacitance value per size of the capacitor, it's really big. So to cancel out this inductor, you need a fairly large capacitor. And having a controllable capacitor inside the rotor is not doable. You don't have you need air gap, you need isolated, you need pretty big bulky capacitor. So that's what's too hard to do. But so type 3 did not do that. What type 3 does is to look at this and says, well, this is I don't actually need to add a capacitor. Because reactive power, again, is not work, right? So there is a conservation of reactive power, but you can get free reactive power by adding capacitor. But type 3 simply says, what I need to do is I need to change the angle of the current coming out here. So the problem with this one is the voltage is always in phase with the angle. If you look at this as a developed voltage, since this is purely resistive, it's a negative resistance, but still a real number. So this current and this voltage developed are purely in phase. They cannot get reactive power out of this. The idea is if I can change the phase of this current or this voltage, then I can get reactive power. Then I can potentially cancel some of these sort of inductances out. Okay? So that's type 3 idea is I don't need to sort of have more power. I don't need to develop more power. I just need to change the phase. And the way to change the phase is by having a voltage source. So type 3 is to say that, well, so what if I don't add a resistor? So this is my current. So this R1, X1, X2 prime, R2 prime. The idea is, can I add a source here? Okay, so we're going to add some voltage source. What this voltage source does is not going to fundamentally change where power comes from. Power still comes from what? It's kind of induce a phase change. If I can change the phase, then I can provide reactive power. Okay, so that's the idea of type 3. Okay. And again, the benefit is this thing basically gets divided by S. Right? You have a slip. So any voltage you add here gets divided by S. So that has amplification effect there. So you get pretty, so even by adding a small voltage, you can get a big effect on the circuit. Okay, so type 3, this is called the more common name, or I guess equally common name you'll see for type 3, is this DFIG. Okay, so induction generator, IG comes from induction generator. Doubly fed, meaning there is 2 paths for current to flow. So we'll see this. Okay, so the important part is the doubly fed part. Induction generator is just a type of generator. And that basically where that comes from is you have a rotor circuit. You have a voltage injection at the rotor. Right? Sorry? You're adding some sort of excitation system, yes. No, except the excitation comes directly from the grid. So it's not as a synchronous generator where you have external excitation system. This excitation comes by drawing another wire from the grid. So it's not a standalone excitation system, right? So induction generator does not do well with a standalone excitation because of frequency problem. You still need to be sort of fairly synchronous. Yeah. Okay. So it's not a DC excitation. The excitation comes from the grid. So that's a good question. Right. So that's a difference between induction generator and synchronous generator. But still here, the main key word is this doubly fed. And you'll see this a lot. Like this DFIG, still most of wind turbines are this type. They're sort of fairly robust design type. Okay. So the idea is again basically add a voltage source. Okay. So in type 2, so what happens in type 1 and type 2? This is shorted together. Type 1 and type 2, you short this. It's just a rotor. There's no outside connection. In type 3, you have a connection coming from the grid. So you have a connection going to the grid. You can think of this as a current connection coming from the grid. So there is a wiring on the rotor side. So we'll explain, so this is, right, so this is our sort of a, the connection we have seen before. So this is the rotor connect to the grid. Okay. So this is, if you want to look this part of the system, you're looking from the rotor to the stator to grid. And then from the rotor side, what we do is we add something called RSC. So what is RSC? RSC is basically a converter to the rotor side. Okay. A converter from the rotor side. And this basically has some power coming from this converter. So the power balance now becomes, I have some mechanical power coming in. This mechanical power is coming from the gearbox, coming from wind. There's some power going out to the grid. There's some power going out to the grid. I'm generating power because I have a negative slip. There's some power coming in or out from the rotor side converter. So this, the sum of this could be positive or negative, again, depending on the phase. Okay, so it's a, so the power balance is now have three powers. But before was the PM, so the mechanical power coming in, there's some losses and the power goes up. Now this mechanical power comes in, there's some losses. You add the power coming from PR, that's the power going out. So if you draw the diagram, this is what the thing looks like. Okay, so this is what the whole thing looks like. As this is our grid. So this is the three-phase connection to the grid. You have wind power coming in here. And then we'll connect the grid back to the rotor. We're going to connect the grid back to the rotor. And we're going to do this connection basically through a AC-AC transformer. Okay, so the way to read this connection is, well, you need a transformer because this typically steps down voltage. So if you look at this way, this is step down voltage. Okay, this transformer steps down voltage. Then goes through a AC-AC. It goes through, you convert this to DC and going DC back to AC again. And then this gets injected into the rotor. Okay, and then power can flow this way as well. So this is PS. You can think of this PR coming in at the rotor side. So what is the benefit of this sort of, AC to DC, DC to AC again? Okay, so what does this converter do? So you see it, if you see this kind of setup, what are we trying to do? Have a converter like this. Right, change the phase. Right? This is what you do is you try to change the phase here. Because once this gets to DC, there's no notion of phase anymore, just a DC current. Once you convert back to AC, you have to control the phase actually by yourself. And that's a free variable you can change. Okay, so you can change the phase from this link, and then allows you to control the phase here, and that will change the current flow. So you can think of reactive power coming in this way. Or in some sense, if you get the phase correct, you have reactive power flow like this. Okay. So this connector is to change the phase. Okay, so this is the phase shifter. Okay, so this allows you to basically, so the voltage source now developed in this rotor can have a different phase in the current coming out. And you have this, right, V times I, you have the angle between them, but based on this angle, you can generate reactive power. Okay, so that's a main sort of conceptual setup of a DFIG. So the double effect comes in this. You have two paths of power flow. So this is your double effect induction generator. Questions about this setup? Yeah, so we'll get to the fault protection later. So this is The fall protection is a little bit trickier for this, a little bit trickier. But let's say in normal operation, this is the idea for the generator. Okay. All right. So the main reason it took us many years to get to this. Go ahead. Yeah. Yeah. Yeah, you have to line the frequency, but that's pretty easy to do. So the frequency lining up frequency is pretty easy. Because the grid is normally, so you have a measurement here, right? You can measure the frequency of the grid. So you know exactly what the frequency here is. So you can have a pretty simple feedback controller tracking this frequency, right? So that's easy to do. So you have a phase lock loop. Basically, you have a phase lock loop. You lock onto this phase here. And this, so you lock onto the frequency here. The frequency doesn't change all that much on this grid. So the frequency change is sort of slow. And then your power electronics is normally much faster than this frequency change. So it's easy, sort of easy frequency to measure. Good question. Yeah. So that again goes back, why did this take many years to develop? So this concept is not new, right? So, you know, when people were designing wind turbines, this was proposed, right? What you need to do is you need to change the voltage and angle phase, right? So this is one way to do it. The reason you have to wait many years is you have to wait for these to be high power enough and to be reliable enough. And then as you said, for the control to be good enough to track everything. So that was what we're waiting for, right? You need your controller to be good enough. You need these to be sort of reliable enough under high power operation. So just to get an idea of different power flow. So how much power do you think flow through this path versus this path? Like what is the proportional power flow between these two? Any guess? So yeah, so if you look at this, you will think most power will flow through here, but that's actually not the case. For this to provide reactive power, about 1/3 of active power has to go through here. It's because there's a lot of reactive power element here. So you need sort of not insignificant current to go through this side. Okay, so you need some current to go through here. You need some current to go through here. So the power division from this is normally you have 2/3 of the power. Here you have sort of flowing out this way, you have 1/3 of power flowing out this way. Okay, so for let's say for a 3 megawatt turbine, this is a megawatt. Okay, so you need, these are not small things. Okay, so you need this to megawatt level or hundreds of kilowatt level converters. Okay, yeah. Sorry? Yeah, yeah. So you need the current to be fairly large. Yeah, you need some current. In active power also has to go out this side. It's hard to design a case where it's no active power going out this side. So you need active power to go through both, and you have about 2/3, 1/3. In sort of modern turbine, this is how the balance is. So these are big, like these are big things. So you need to wait, so basically in the 90s, we could build these, and the controller was good enough to do control. And if still today, if you work on wind turbines, a lot of work still happening is how do you design a better controller for this under different circumstances. What if there's a fault? What if there's a short? What if you want to temporarily provide more active power? This kind of things. There's a lot of design still going up. Most comes from designing these converters and the controller for this converter. Right. So these are converters. Again, these are 3-phase converters, right? So I'm just going to draw here reference diagram for 3-phase. Okay. So on the rotor side converter, what does it do? Well, there's some developed torque. Okay, let's try to control the reactive power flow. Okay, and let's try to sort of control the direction of current flow on the rotor side. And the grid side converter, what you do is you keep the frequency synchronized to the grid. You try to keep this voltage constant between these converters, and then you balance some reactive power through this. So again, these two are two sides of sort of, this is trying to do a best job converting the torque to power as best as you can. This guy is trying to maintain this voltage. So you see a constant voltage here. And then synchronize the frequency with the grid. So there's a lot of synchronization going on here. Okay, so feedback again is very, very important. So I'm not drawing any of the control circuits. If you take power electronics, especially the graduate level course, there's a lot of things about control here. So I'm not going to draw any of them, but just in the background, that's where most actions happen. Okay, how do you switch? How do you control? We're going to assume that all these are done sort of fairly perfectly in this diagram. Right? Any other questions? Okay, so this is our sort of components in it. The equivalent circuit will be pretty simple. Okay, so let's say, because what we do is from the rotor side, so for equivalent circuit, all I care about is, this is my induction machine. What does it see when it looks like this voltage? Okay, from our equivalent circuit, so our circuit is entirely here. We're not gonna model this. This is a bit too complicated. We want to do actual model. So our circuit is here. Oh, this circuit sees that, oh, there's some voltage there. Okay. So there's some voltage on the rotor side. So the equivalent circuit is not a lot of change to the circuit we had before. Okay, so we have the same circuit as we had before. We have X2, R2 prime. We have a developed voltage here. And then all we do is we add this. Okay, so this comes from the connection, right? Coming from the connection to the grid. So this is R1, X1, XM, X2 prime, R2 prime. And this developed voltage is still here. This is okay. So again, all it changes is you have added voltage source that's coming from the grid. And your job is to mix this voltage source, right? Your job is to set this thing such that you have desired behavior out of this circuit. And that's the equation we want to solve. So this is normally a phasor. You can set a different phase for this voltage. Okay, so if you have this circuit, right? So this is a circuit we have drawing again. Okay, so you have all this different kind of power flows here. Right, we still have I2 power flow, we still have I1. So if you look at different loss, right, you look at different parts of power, then what power we have is this. This is our let's see. Yeah, so this is our PR. Right? So you think about power flow, this is the power coming from the power electronics side. So again, this could be positive or negative. There's really no sign, there's no predetermined sign for this. This could be positive or negative coming from power electronics side. Okay. This developed voltage, this is our PD, right? So this is the developed power we had from before. This is PD. This is our loss, right? So this is one loss we have. This is PCU2. This is PCU1. And this is the PS power we have. Okay. So same, almost the same power flow as before, except you have this added power here. Okay. Right. So this power, positive or negative, gets added to the developed power, gets lost here, gets lost here, and come out. Any questions with this power flow? Okay. So again, we're going to go back to the induction generator equations, update all the equations by accounting for this additional term. Here, right? So we have all those equations before. When we had the added resistance for type 2, we add some equations. So here, when we account for the added fact I have a voltage, first I'm going to add another term to all these equations. Okay. So just before, again, often we'll take a simplified model. We'll ignore the state. We ignore the stator part and just look at the rest of the power. So especially for dFIG, a lot of times the equation can get fairly complicated. So we'll just ignore the stator side and then look at the rotor side equations. So here we have I2. Right, so here again, you have it's exactly the same equation as before, except instead of 0, minus VA1. Now you have this VA2 prime over S minus VA1. This is your current flow. And I1, minus VA1 JX. Okay. Any questions about this? Again, same equation as before, except you have this new term coming. Right? So that's our equations. And now we're going to look at the power flow diagram again. We're going to look at how does developed power change to air gap power, change to stator power, change to losses, and look at through all that diagram again. Okay, so power flow, again, drawing this again to remind us, our goal is to track where the power goes, track different terminology, and look at their relationships between different powers. So this is our, so again, we'll start with some input power. Okay. So think of this P in as a power coming into the rotor from both the mechanical power from the gearbox and injected power coming from the grid. Okay. So think of this as a total power that's coming to my rotor. And we want to compute how does this thing get divided up. So this has two parts. There is a P gear, the gearbox part. There again, so P gear, there's some rotational losses outside. So there's some rotational loss in the gearbox. That doesn't get to, that power doesn't get to grid. That's the power that lost. And then we have the developed power. And then that's our developed power. So the added branch, that's the injected power. So this will be PR, right? So we're injecting some power into the rotor. So PR, also part of the total input power to the system. These two now get added together. So these two get added together. If you look at this diagram, so that's adding this one with this one. Now I have a loss and then air gap power. That's the power flow. So this power goes to PCU2. That's one the copper loss we have. This is 3 R2 prime I2 squared, right? This is my loss. What's left over is air gap power that goes through into the stator side. And then this gets separated out. This is our PCU1. Okay, so if we have a resistor at the stator side, then this is 3R1, IA1 squared. And then this is my PS. So that'll be my power to the grid. That's a stator power to the grid. Okay. Any questions for this sort of block diagram power flow? Yeah. Still use a gearbox. Still use a gearbox. The power is still generated from a rotating machine. So the gearbox. On top, yeah, go ahead. No, P in is the total power coming to the rotor. So that's a difference in before. It's a total power going to the rotor, right? So this is coming from the grid converters. PR is coming from the grid converters. This does not need to be positive. Right? It's not. I'm not saying the grid is sending power through the converters. It just is easier to think of this some power could be negative coming from the converters. Because we want to read the circuit from the right to left. That's easier to do the loss mechanism this way. So I'm going to add these two and call this is total power coming in. Total power coming in is not necessarily bigger than the developed power. It could very well be this term. By setting the phase, this turns out to be a negative active power. Right? So the grid is giving you negative power. So that means you still have some power flow out of this side. Okay? Because P in is easier to collect these and think of a loss going this way. Because all the loss mechanism happens this one and this one here. Okay. Right. Any other questions? Okay. Oh, okay. So good. All right, good. So where this V2 prime over S comes from is, that's a good question. So let's do this. So what appears as V2 over S, right? So that's it has a slip. So everything is divided by slip. So what does this equal to? Well, this is identically VA2 prime plus VA2 prime S minus S. Which is for the equation, right? So you have a negative VA2 prime coming out of this 1 minus S term. You have VA2 prime, so this will cancel. So the advantage of writing it this way is the way we think about is this exists because I have a slip. So this is why you need a gearbox. You still need a slip for this one. This exists because of a slip, right? This VD certainly depends on S. This term certainly depends on S. So this comes out because there's a speed difference between your rotor and your stator. This exists independently. So even if the rotor and the stator are exactly synchronized, I can still inject a voltage. Okay, I can still inject a voltage on the rotor side, even if there's no developed power. I can still inject this voltage. Okay. So that's why it's sort of good to write out PR this way. Think of this is purely coming from because I have a path from the grid to the rotor, not due to the fact that I need a slip. This is because I have to have a slip for this thing to develop some voltage. Yeah. Yeah, right there.
So it doesn't have any
Yeah, so the direct drive turbine, this still needs direct drive turbine. Yeah, so here the frequency matching still comes from the gearbox. Yeah, so the gearbox still does most of the frequency matching. Yeah. Any other questions? So that's a good question. Any other questions? Okay, so again, this is DR power exists because I have a non-zero slip. PR exists because I have a voltage connection. I have a connection to the grid. This thing will be there no matter what. This thing has a dependence on S. And the trick again, right? So the trick is this trick. This is actually quite a useful trick in Induction Generator. As you can separate out this 1 over S by this equation. So we do this, for example, by R2 prime, right? We have R2 prime over S, you can separate out to the 2 parts. So this is the same trick. So at the end of the day, this sort of accounting in some sense, right? Inside the machine, you can, so the math is equivalent if you just add it together, but accounting wise, this is easier to think of. So this. All right, good. Okay, so any other questions about this? Okay, so just a bunch of equations now to keep track of, right? Because let's look at PR, right? So let's look at the PR. So this is 3 IA2 prime, VA2 prime cosine theta R, right? Because now what I can do is I can change this angle. So I have some inductive power, depending on what the angle is. It could be positive or negative. So the PD part is more interesting. So if you look at the developed power, again, now there's two components to it. One comes from the VD, the developed voltage, coming from R2 prime, one coming from VA2 prime over S. So there's two components to it. So this becomes 3 VD prime cosine theta D. There's one part. The other part is plus 3, the real part of VA2 prime S1 minus S IA2 prime. Right? So that's just the current times voltage times current part of it. All right, so this is our equation. So for PD, you can write PD also as, because we know the angle, right? So because this developed voltage is always in phase with this current, right? So this is again the developed, this is a purely negative resistance. This purely negative resistance. This is always in phase. So you can write this as minus 3 RD IA2 prime squared. This is as before, this is R times I squared because they're always in phase. Plus 3 VA2 prime S1 minus S IA2 prime cosine theta R. So this to our same equation, just identifying these two will always be in phase. The phase difference, right? So the phase difference across this current and voltage still theta R. Right. So this is what you get to play. In practice, you got to play with this number and this number. You got to play with these two numbers. So PG, this is PD plus PR minus PCU2. Right. So this is air gap power. Any questions about this power equations? Good. Yeah.
Power. So the VA2 prime is not divided by S, right? It's just the value of that voltage because all the S comes after.
Yes. 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 Inductive power. Yes. So inductive power is there's no division by S here. This S is put entirely to this developed power. That's what it is. Okay. Right. Okay. So these are the equations we have, right? So for this power flow. So the type of questions will be very similar to before, except I had this one here. Okay, so common question before you'll see this is slip, calculate power. Now you'll see there's some slip, and VA2 prime is this with the angle of how many degrees, compute power for that. And that's just the equation. So the S here now can be pretty big, actually. That's now can be pretty big. So this is replacing type 2. So type 2 regulated the speed by adding resistance. This will regulate speed essentially by changing these two numbers. That will regulate speed. Yeah, so there's still a much wider operating range. That's a good question. Okay, all right. So yeah, so that's so this type 3 replaces type 2 in that regard. And also does reactive power. So that's why you very rarely see type 2. That's sort of entirely replaced type 2. Came into the market. Okay. All right. So this diagram also give you, so before going next step, again, one thing I'll say is this also give you some of the complexity you have in this equations. Because a lot of questions we ask in your homework and in exam is going in this direction. So given our numbers, compute all the power flows and see what the power flow is. In practice, you don't do it this way. But in practice, you do it back this way. I want some power coming out of stator. Okay, this is what I want. S changes because when speed changes. Now go backwards, compute all these things. So you have to solve a nonlinear set of equations in practice to make this work. Because your control variables are here. And this is an equation that's not so nuts. Especially you have this thing here, you have this I again here, there are complex numbers all involved. So in practice, going backwards, that's not trivial to do. That's not trivial to do. Okay, so our equation, so when we do calculation going this way, but thing to remember is, again, to operate this kind of turbines, you actually need a fair bit of real-time computation for this to work. And you're always computing backwards in practice. Okay, yeah. Right.
So where does that given your code performance all that stuff, where does that power come into this? That power or is that something?
Good. Okay, yeah. So what you normally read out to do is from the grid perspective, right? I got two powers. I basically got PS plus PR. So from grid perspective, I normally want to keep this constant, or the sum of the two constant. So how does changing wind speed impact the power generate? As changing wind speed shows up in a changing S. That's what it shows up. Shows up in a changing S. So we'll change the developed power. Okay, so the changing your developed power will change your power to the state. But I want to keep this constant. So now I need to change VA2 prime and theta R. But changing VA2 prime and theta R changes PR. But then I want the sum of the to be constant. So you need to solve a set of equations to figure out the right one. So for each S, each amount of power the grid wants to get, there's some VA2 prime and theta R. There's some VA2 prime and theta R for each particular S, and each particular power I want from the wind turbine. And in real time is normally this one subtract this one kept constant. S changes all the time. So for changing S, this part of the equation changes, and your job is to change this number to still track this target. Does that make sense? Yeah. So yeah, go ahead. Yeah. Oh, so that's the amount the grid gets. So that's a good question. So if you go back to this diagram, okay, go back to this diagram. So this is PS and PR coming here. So when the grid operates by normally demanding a constant power output. The thing is you have a generator. From grid operators, for example, I allocate resources. So this generator will provide 2 megawatts. Right. Well, I want this generator to be a constant power output. So I want these two sums to be a constant. Right? But then S changes here. So I need to track them. Any other questions? Okay, so if you taking control classes, most of the system you control will be a linear system. And then tracking will have all these nice controllers, can be nice controllers. This is an example of a pretty nonlinear system that needs to be tracking real time. And again, stuff still go wrong in this kind of tracking. I have a large enough perturbation. It's not clear what happens inside this turbine because the systems are nonlinear. So it's still not trivial. It's still not a trivial problem. All right. And nowadays, if you look at so before when wind turbine first came online, the grid made a lot of allowances for wind turbines. So you're allowed to vary your output, right? You're allowed to throttle whenever you want. The rest of the system will kick in and back you up. Nowadays, if you're wind turbine, you have to behave. There's a lot of constraints on how you behave. So it's up to you to do this tracking for the grid. So the grid will not tolerate a variable generator anymore. Okay, so it's a grid, because there's a lot of wind. If all the wind decides to ramp up and down 20% all the time, then there's not enough other resources to back it up. So now you have to be pretty firm, right? You have to, as a generator, you have to be fairly firm. And then there's sort of, it's getting fancier and fancier, this path. There's a lot of fancy control in this path. Okay, so that's the idea. So for us, it's mainly understand all these equations and working through them. There's just a lot of power to keep track of. There's a lot of power equations to keep track of. You often, when you're doing a homework question, is knowing what is what. Like what exactly, which one of the equation is the question asking for. And that's where it takes most of the thought. Okay. So again, if you look at so there's a equation that people like to define. There's a common power in addition to all the ones I'll show you that people like. And so there's just, they're just part of the, I guess, subject. As if you look at the air gap power, look at this air gap power, it's PD plus PR minus the copper loss, right? So what we want to do is we want to define another power called Pslip. We want to call this thing Pslip. And this is just I guess the terminology we use, because we want to write the air gap power as a combination of two terms. Okay, so the goal is to write the air gap power as a combination of developed power plus some other term. This term lumps the loss you have and the injected power we have. Okay. Right. So yeah. So what this allows for you is, without this injected power, you just have air gap power is always PD plus a term. Now, even with this injected power, we still want to talk about PD plus a term. We're going to lump this and call this Pslip. Call this Pslip. Okay. So this, we call this Pslip. And then the reason we call this, so Pslip also have a fairly easy formula that you can compute it with. Okay. So what Pslip has is, there's an easy formula for it. Because if you subtract these two, you subtract PG from PD, you do this subtraction, and then you look at this in terms of torque. Okay, you look at this in terms of torque. Right? So what we want to say, right? So the way torque calculation is about is, now the diagram becomes, there is a rotor. Okay? There are some rotors spinning at some speed, omega-2. This gets into some stator, this crosses the air gap. This is our air gap. This thing is now spinning at a synchronous speed. Okay, so the power it's useful to think of the power as a torque times frequency. Torque times frequency. So the power here will develop torque times this frequency. Once this thing goes across the air gap, well, this will become develop torque times the synchronous frequency. Okay, this is the so the torque times frequency, this torque times synchronous frequency. So where did the power go? Okay, so there's some power loss. And this thing is called Tslip. So think of this is the power that gets lost when it goes through air gap. The power gets lost because you have a slip. And some power that's went away. And then if you do the subtraction, you have a very nice subtraction. You can pull TD out by definition, same developed torque. Subtract these two, you get TD S times omega by just the algebra works out. So the slip power is S times the air gap power. So this tells you, again, there is some developed power that gets into the air gap power. Part of that doesn't make it. Part of the developed power doesn't make it into air gap. What is the fraction that doesn't make it? It's S times this air gap power. Okay, this S times this thing. Okay, and this is gets S as a small number. Small part of it gets lost in the set, or gets. I guess there's small part of it as you can think of as coming from the slip. And so this is just a terminology. This is a, and this, what this does is often also gives you a way to think of, this is your loss, this is injected power. So how much power did you inject, subtracting the loss? That's another way to measure how much power you have injected. Okay, this is sort of a good baseline to subtract it off and think of how much power it is. All right, so this is our Pslip. And then you can write out, because Pslip is S times PG, by definition, PG is PD plus Pslip. So you get an equation that PD is PG times 1 minus S. So this is the equation we always have. Right? We always have this. In type 1, type 2, type 3, we always have this equation. So this is a good equation to remember. It's a very useful equation to know, to remember. For example, in this last week's homework, I believe, basically a question about given air gap power, can you compute valve power given the slip? Right? So it was to use this equation. Okay, so this is just useful equations to know. All right, so any questions about this? Okay, so just a bunch of equations. So here is just redrawing the diagram we have by dividing up the injected power into a slip power and the copper loss. So the same diagram drew again, separating, accounting for power another way. All right, so yeah, so when you're doing homework, so you'll be looking at this diagrams a lot. We've become very familiar with these diagrams, computing which power is which. Okay. So now this is a good time to, I guess, take our break. After that, we'll look at, by changing VA, what happens to the operating characteristic. Let's take a 10-minute break, come back at 9:35. And so by changing the voltage, you get to shift this curve this way. So for the smaller voltage, the more the curve shifts this way. Okay, so you have a pretty wide range of operations by changing voltage here. And this while changing the operating characteristics is more efficient. Again, you're not changing a resistance, right? Changing the voltage. Okay, so this is not losing power. Right? The power is not lost. Okay. Again, even if the injected power is going from the grid to the rotor, that still has to come out on the stator side. Okay, so when you have a resistor, that resistor has to lose power. When you don't have a resistor, the power has to come out somewhere. Right? So this is more efficient. Yeah, so let me just plot the curve here. The actual analytic relationship is quite difficult to get. But just think of by changing this voltage levels, you can shift where this maximum occurs. Shift this maximum. So the P max, the pull-out power, depends on VA2. And changing VA2 changes the operating characteristics. Okay. So let's do one example to put all these equations to use. Okay, so here we have a 6-pole, 60 Hz, Y connected, terminal voltage. Okay, so we have an effective turns ratio of the generator. So just put in, make things a little bit more interesting. The rotor parameters are the following. Okay. And then we're going to inject this voltage. Okay. So this voltage, you need a reference, right? When we talk about complex voltages, we need a reference. And the reference is typically taken most of the time with the stator voltage as a reference. So VA1 will still be the reference most of the time. So we're going to develop this voltage with a pulse-width modulation technique. So somehow I can give you this voltage. And then compute develop power, develop torque, rotor injected power, stator power, and this. Okay. So we're just putting all those equations into use. Okay. All right, so let's again draw the circuit diagram and look at all those equations. Okay. So this is a very complicated, not very complicated, but fairly complete example because I have an XM. Okay, and the question did not say ignore XM, right? We have R1, R2 prime, X1, X2 prime, and Xn. So first, we're going to do a summoning equivalent calculation, right, just to show you all this kind of thing, right? So again, you may not get a question that needs the summoning equivalent, but the question doesn't say ignore these parameters. We still need to do that summoning equivalent calculation. So this is our VA1, R1 X1, XM, developed voltage, our VA2 prime over S here, okay. X2 prime, R2 prime, IM, X1, R1. Okay, so this is I2 prime, this is I1. So let's do a summoning equivalent, right? So do a summoning equivalent for this to be able to compute I2 prime. So VTH is JXM, VA1, R1 plus JX1 plus XM. Plugging all the numbers, we get 386.7 angle 0.056 degrees. Okay, so this is, right, so what you do is, when you compute the summoning equivalent, mostly this shot is not going to matter too much. So this angle will be small. This number will be very close to 690 divided by 3. Okay, so that's just a sanity check to see if you've done the equations correct, right? So these are the voltage. Now let's compute the summoning equivalent impedance. JXM, R1 plus JX1. Putting all this together, 0.1457, angle 88.15 degrees. Okay, so this is the summoning equivalent voltage and summoning equivalent impedance. Okay. So then let's compute the slip, right? We always need a slip to do this question. So NS minus N or NS, 1200 minus 1230 or 1200 minus 0.025. So this is our slip, and we have our basic circuit set up. Okay, so now let's compute IA2. Let's compute IA2. So when we compute IA2, what the circuit looks to us as, I have a summoning equivalent. I have a R equivalent, X equivalent here. Or let me draw this. Let me draw this a bit more in detail. So we have a summoning equivalent voltage of RTH, XTH, X1, X2 prime, R2 prime over S. And here we have VA2 prime over S. Right. So this is our circuit. And now I want to compute the current IA2 prime. Okay. And so the current computation is just this voltage minus this voltage divided by all the impedance altogether. So IA2 prime is VA2 prime over S minus VTH divided by everything. So here I have RTH plus R2 prime over S plus J XTH plus X2 prime. Okay, putting everything in. All right, so then substituting all the numbers into it, we get 945 angle 25.48 degrees amps. Okay, so that's our I2 prime calculation. And then from I2 prime, we can compute a lot of powers. in the system. Okay? So all this question goes fairly similar way. You find an equivalent circuit, you compute the current, and then from the current you compute all the powers. Okay, so now let's compute the developed power and the developed torque. Okay, so let's do all these calculations. So the developed power, again, let's remember where the developed power comes from. Developed power comes from when we write out the block, as we have a VA prime S1 minus S. So this is one part of the developed power. This is coming from VA2 prime. And another part of developed power, this comes from VD. This is R2 prime as 1 minus S IA2. Right? So developed power is how much power gets developed in these two things together. Okay? So we can go back and look at our equations. This developed power is PD is minus 3 RD IA2 prime squared plus 3 VA2 prime S 1 minus S IA2 prime cosine theta R. Okay, so this is our calculation, right? So the first part is pretty easy. We know what RD is, we know what IA2 is, we just computed. The second part is a bit more interesting. Now, what is the angle difference, theta R, between the voltage and the current? So that's an interesting part. What is the angle difference then? Okay, so you have VA2S, you have VA2 prime at this voltage with the angle of minus 120. You have IA2 with this angle. Right, so this is another angle here. Then what is theta R? So theta R is normally the least obvious calculation to do. Everything else just plugging the numbers. But how about theta R? What is this value? What is now the angle difference between the injected voltage, VA2, and the current? Right, so there's a voltage angle minus the current. Right? So remember, both of these are referred to the state. So they have the same reference. Okay, so you can subtract them, use the normal intuition, subtract. Okay, so this is minus 120. That's your voltage angle, right? We have VA is minus angle minus 120. Subtract the current angle, which is 25.48 degrees. Okay, so this is your theta. Okay, so that's the key thing to remember when you do this calculation. This is not the angle of the current, for example, because this is a relative angle between this voltage and the current. Okay, the voltage angle is something, and then current angle is that. Right? So you take the voltage angle, subtract the current. Okay? So both of these, so all the angles here refer to the state. Okay, so you need to subtract them. Okay? So that's really the non-trivial part. Everything else is a straightforward plug into the equation and see what comes out. This will be 1.028 megawatts. Okay? So this is, we plug all the numbers S and IA2 into this equation. That's the equation. All right, so this is our developed power. And then the developed torque, this is PD over the speed. This is, by definition, the developed power over the speed of the rotor. So this is PD over 2 pi times 1230 divided by 60. You get 7.98 kilonewton meters. Okay, so that's our developed torque. Again, when you do questions, especially in the midterm, this angle trips up a lot of people because people either think this is minus 120 or think this is this angle, or instead of subtracting, adding the angle somehow. Okay, so don't think, just follow this equation. Don't have an idea what the angle should be. Okay? So if this is a very negative angle, it's fine. It could be a very negative angle. All right, so this is our developed work, right? So now let's compute the power to the stator. I want to now compute the power to the stator. Do I need to compute IA1? Okay, so now we sort of unroll the Thevenin equivalent circuit, VA1 here. I am here, you have IA2 coming in here. So the question is, what is IA1? Right, so how much current do I have left of IA1? Okay, so now we can set up an equation, uses Kirchhoff's voltage law. So VA1 is minus R1 plus JX1 times IA1 plus the voltage rise across the shunt element. Okay. So the idea is I want to solve for IA1. Okay. I want an equation where I can solve for IA1. Okay. So this is a useful equation because I know this number, right? So the voltage at the grid side is always fixed. Okay. So I know this number. So I can keep writing this. Well, this is X1, IA1. So I know JXM. Well, what's IM? Well, IM is simply IA2 prime minus IA1. Right. So this is Kirchhoff's. So this is the current balance law. Okay, so now we have an equation that's in terms of IA1. Okay, well, it's equation in terms of IA1. So rearrange this equation. We have IA1 as JXM, IA2 prime minus VA1 divided by R1 plus J X1 plus XM. So this is 953.3 angle 29.7 degrees. Okay, so this calculation can seem a bit complicated, but really it comes from setting up an equation for IA1, rearranging this equation, putting IA1 on the left-hand side, everything else on the right-hand side, and then this number comes out. Okay, so all right, so this is our IA1 calculation. Now we can do the stator power calculation, right? So we can do the stator power calculation. This is PS, power coming out stator is 3, IA1, VA1 cosine theta. So here again, the angle is very easy to determine because the VA1, the gray side is always angle 0. Here you have angle 29.5. So that's the angle we have. Putting everything together, we have 989.63 kilovolts. Okay. So a bit of power, where's PD? So a bit of power got lost there, but the stator still, PS still has the, so it's a little bit less than PD in this case. Okay, so let's do this. Yeah, go ahead. Stator is, so angle stator is minus 27 point. Okay, so 0 degrees minus this. So it's a voltage angle minus the current angle. So 0 minus this. Good. Any other questions for this? So this is actually a fairly tricky part. So again, when you look at it in class, seems okay, this equation, just forward, just rearrange it. When you do your homework on your own, this can be tricky. Again, a lot of mistakes made in this one. So always have a good sanity check. The numbers in the problem are set up such that this is not very different than developed power. Okay, so if you get some number here that's very, very different than developed power, probably a bug somewhere. Right? So just have a sanity check in mind. Okay, so there's a lot we can do. So this question really shows all the things you can compute. So this is a good example to remember and study. So study to look at. because it was, you can compute more things, right? I can compute the power losses. I can compute the slip power. And the one thing you want to know is the injected power flowing from the grid to the rotor, or is it from rotor to the grid? That we have not answered. I have computed the developed power. I have computed power out of stator. The question is, what is PR? What is the injected power? Is that positive or negative? Is that which way is it going? Okay, so let's compute the losses, right? So let's compute right. So we can compute the loss. We can compute the slip power. We can compute the injected power. So it's computing everything. Copper loss in 1 is 3R1 IA1 squared. 13.4 kilowatts. Okay. So PG, what we can do is, so I can compute air gap power. PG is the power to the stator plus the power lost in R1. This is 1.003 megawatts. Okay, so this is the air gap power. Now we can compute Pslip. Okay, so this is how we're Pslip something. This is S times PG. So this is we want to compute. S is a negative number, right? So S is a negative number. So this will be a negative power coming out. This is minus 25.1 kilowatts. So what equation we really want to use as PR is Pslip plus PCU2. Right? So this is really the thing we want to compute. So PCU2, this is 3R2 prime, IA2 prime squared. This will come out to be also 13.4 kilowatts. And we add this two together, you get a minus 11.68 kilowatt. Okay, so you get minus 11.68 kilowatts. So there's a negative sign. So which way is the direction going? This is the answer you get. Is it from the stator to the grid or from the grid to the stator? So let's think about this definition of this, right? So let's look at our diagram. Okay, let's look at this diagram. Okay, so basically PR, right? So PR drawn this way, we're drawn this way. If this number, so what this number does is this is the power coming from the grid to the rotor. So this is a positive sign. Right? This is how you take power from the grid, you inject it to the rotor. Okay? The rotor gets two powers, the developed power and this injected power, added together. So the positive sign, so PR has a positive sign, it's just going into the rotor. PR has a negative sign, means it's coming out of the rotor. Okay, so that's the sign convention, this works. Okay, so in this case, because the sign was negative, it's actually power from the grid. So this is power from the rotor to the grid. Okay, so because in all the equations, the PR was assumed that this is power to the rotor. You're adding power to the rotor, this gets into the air gap and coming out of it. Okay, so because it's negative, this is the rotor to grid flow. The rotor to grid flow. Okay. Right, so this number is quite a bit smaller than PS. Again, in practice, this number will be quite a bit larger, but then the other numbers will be less friendly. So the question itself that for other numbers look nicer. So this will be a very small number injected power. Okay. Yeah, good.
This problem, the angle theta S was, wouldn't you want the theta S to be as small as possible, ideally, if you have a close?
Yes, you want to measure theta. So here the theta is still quite big. Yeah. So it's still quite a bit of reactive power. Okay, good. Yeah. So here we did not regulate. So as we do more calculations, you'll see this question again getting turned around. Because here is given VA2 prime with this angle, compute everything and compute. Right? Later we'll see questions where, as you said, let's say I want. Right? So you can have questions. I want this theta s to be a particular number, say 5 degrees. Go back and compute everything else. Okay, that's another example. Those questions can complicate very, very fast. Okay, those without sort of fairly, actually, yeah, without fairly sophisticated programming techniques, those get very quickly. Okay, so we'll see sort of simplified version of that. Okay, so imagine reversing this calculation, especially fixing an angle. That's too complicated. So when we do calculate, when we go backwards, you'll see a lot of different assumptions. Saying, oh, assume this curve stays constant. Assuming this angle doesn't change, then compute what happens. Those are made so you can do the problem. Okay, those are made so you can do the problem. Otherwise, going backwards is way too complicated for us at this stage. Okay. Good. Any other questions? Sure, go ahead. Oh, that's a pretty high curve. That's pretty high curve. That's pretty high curve. Right. So normally, yeah. So normally, as this angle is all quite high, we want this angle to be small and this current to be small. Okay, so normally that. But that, yeah. So the other numbers, so 120 would not look so nice. So this question is, I pick 120 and 5 to be nice numbers, then that's where the current comes from. Yeah. Go ahead.
So this is a case scenario where we have
yeah, you can have that by changing the angle. Oh, this was not a negative 120. That angle was smaller. You could reverse power flow. That's fine.
That's meaning we are not injecting reactive power, right?
No, you can inject active power going from the grid to the rotor. That's fine. Then that will come out as PS. It's okay. So you can inject power that will come out here. Yeah, the power has to come out somewhere. It will come out as the stator side. So you can cycle active power down, actually, if you want. You can cycle it from the grid through the rotor coming out of the stator. Oh, so what happens is, so let's say I want this, so this angle is positive, right? If this angle is positive, am I consuming or generating reactive power? Which way does reactive power flow go? If the current is leading. Are you generating or consuming reactive power?
No, consuming, right?
You're consuming, right? So they're consuming. So let's say you want to generate active power. So you want this actually angle to be negative. Then you can have scenarios. Because you want reactive power, you want to provide reactive power, you have to cycle active power, depending how the angle works out. So that could happen. That could happen. Okay. But normally you can, right? So you can either control active power or reactive power, but you cannot sort of consider everything. So you say, okay, I want reactive power to come out of this, then maybe active power will cycle. Okay, so that could be a scenario that happens. You want to avoid that, right? You don't want to cycle too much active power through the circuit, but still sometimes it's not avoidable. Right, for example, this allows you to do things like, okay, there's no wind. There's complete or very little wind. But still want to reactive power support. You may just have to cycle active power. Look like an actual cycle. Through the power electronics will change the angle and this comes out the other side. So all that is potentially possible. All right, good. Any other questions? Okay, so this shows again all the forward calculation. This is the forward stuff. So if you look at the direction of power flow, be more explicit is if you're operating at super synchronous speed, or you're operating at the speed that's faster than the synchronous speed, this means that will basically give you power from the rotor to the grid. Okay? It will give you power from rotor to the grid, the PR side, because PS, so assuming this is a positive number, PS is a positive number, you multiply by a negative number, so this is negative, that means rotor to the grid. Which sort of makes sense, right? I'm faster than synchronous speed, I'm generating active power, the active power comes out both sides. Okay, active power both sides. So that's one, that's sort of, right? So of this is a not a, so you have to worry about, so this doesn't get negative, you have to be careful about this. But assuming PS is positive, PR will be a negative number. Okay. So this is normally a rule of thumb. Okay. But if it goes the other way, of course, power can flow from grid to the road. Okay, so this lets you use this as a machine. If you're operating less than speed, you can be a machine. That's fine. Power can flow the other way. All right, so now let's do a reactive power accounting. Okay, so that was active power accounting. So now we're going to do a reactive power accounting. Okay, so before we started for a induction machine, you can only consume reactive power because all of these are inductors. Now you have a benefit of this reactive power source and this reactive power source. Okay, so they could provide reactive power for all these inductors to consume. Okay, so you can sort of lessen the amount of reactive power you need from the grid, or then provide some reactive power. All right. Okay, so the way you can balance reactive power is the following. So we're going to do this calculation, and reactive power comes again from two sides. You have a QR reactive power coming from one side. You have QS coming from the grid. Okay, so the grid is going to supply or potentially supply some reactive power. But again, without this one, grid is supplying all the reactive power. But now we just give another source for grid to supply reactive power. Okay? And hopefully you can set up a angle difference, so this thing will also give you some reactive power support. Okay. So you look at the diagram is you have two flow of reactive power from the stator, from the injected part. And you're trying to balance out all the reactances inside the rotor and inside the stator. Okay, so we're going to do, instead of active power accounting, what we did before, we'll do a reactive power account for the reactive power inside the system. Right, so there is one, let's look at the power through the rotor side converter. Okay, so let's see what happens when we look at this PR. We'll look at this rotor side converter. So all these converters are switching. What happens to our Q? What happens to our reactive power in this sense? So let's account for reactive power. Okay, so let's do that. Okay, so I have SR, right? So now what I'm going to do is I'm going to look at the complex power, or the total complex power coming out of this. So the complex power S R, this is 3 VA prime, IA2 prime. Remember to conjugate the current, right? So this will tell me the active and reactive power flowing out of this. Plus JQR, right? So again, all this computation, you can use the same equation we had before, right? Before, we definitely knew this one, we knew this one, you could do this product to figure out the reactive power coming out of it. And then, so that's the reactive power coming out of the source. There is a QRS, right? So this voltage, developed voltage, still also may generate or consume some reactive power. So this QRS, this is 3 times the imaginary part of VA S1 minus S IA2 star. So this is just the imaginary part of that equation of that voltage source, QRS. So the total injected power, right? So the total power we can think of, reactive power being injected is QR plus QRS. So that's the total amount of power I get from it. And then you can write this, you can sum the two equations if you want. This is also the imaginary part, 3 times 3 VA prime S IA2 prime star. Okay. So these are equivalent equations, right? So this is again playing the trick of VA over S as VA plus V over S1 minus S. Okay. So physics, right? So I have a source with a voltage of VA prime over S. I have some current develop here, modify them together, conjugate, and you get the image. Yeah, go ahead. Yes. Conjugate. Yes, don't forget the conjugate. If you don't want to make this assignment, yeah, don't forget the conjugate on the currents, conjugate everything. Good. Okay, so this is balanced out, right? So what we have is so the total power that gets provided, total reactive power gets provided is equal to the total reactive power consumed. So I have three inductors, this one, consume reactive power. I have a source, source from here, source from here. So they add up to be the same. Okay, so one way we want to write this is we're going to write this as QR over S. Okay, so we're write this whole thing as QR over S to pull this 1 over S outside. Okay, so this is QS plus QR over S equals to Q1 plus Q2 plus Qn. Or the amount of power I need from the grid is reduced by QR over S. This is the amount of power I need from the grid reduced by this much, because I have QR over S. Okay, any questions for the equation? So again, the benefit of having this injected source now is this is more explicit, is you get to divide by this small number. You get to divide by this S, which is quite a small number, right? And this S divided by this small number means that your voltage doesn't need to be that big. And that's why you see a lot of voltage for VA2 prime is like 5 volts, 10 volts. Because divided by S is actually a lot larger voltage than it appears to be. So S still shows up here. Right, so this is the power flow through the rotor side. Okay. We have another power flow because remember the path that the rotor goes in. So this is the three-phase gray side, but now you have a converter here, and you have a gray side converter here. So really, to compute power flow, we need to both to compute the power here, reactive power here, and the reactive power coming out of the gray side converter. Okay, you need to compute both. And so with active power, you don't care about this accounting for both. That's because you cannot lose active power in this task. Okay, whatever comes out here goes into here. Reactive power is different. Again, because they are separated by a DC link, this block by itself could generate reactive power or consume reactive power. Okay? So this is different between reactive power and active power. You cannot get active power by switching something, doing fancy switching. Reactive power you can. And so that's why accounting is you have to account for this one. We also have to account for this one. Okay? Right. We need to do accounting for both. We are not do that accounting because that requires a different set of equations. And I probably won't finish within the next 5 minutes. Okay, so I'll stop here today, knowing that next class we'll do this accounting from this part of the grid side converter, and together this will complete type 3. Right, there's active power part and reactive power part. Okay, so yeah, so the midterm will cover to mostly type 3, depending on where we get to, and then so there'll be practice questions for type 3 converters. For type 3 turbines, you don't need to hand them in. So I'll release a question and a solution at the same time. But you should at least look at those questions, make sure you can do it. Right, so in the midterm, we'll at least have one question about type 3 doing active power calculation. Okay, but I'll release a question and a solution together. All right. Yeah. It'll be very similar, yeah. So the coding will be solve this equation. This kind of question solve this kind of equation. Yeah. Any other questions? Okay, good. All right, see you guys on Thursday.